I've got Dave, my dad, here. We're going to show you how to troubleshoot when your machine doesn't turn on. This is really frustrating and actually really difficult. Tell me the story. You had this drawing made because you had a hard time troubleshooting machines and couldn't fully understand it and teach people.
We were actually helping write a manual for the federal government, for the Army, so that they could troubleshoot, so they could troubleshoot the machine in a war zone, and they wanted a manual that an 18-year-old in Iraq could fix the machine, which is not very likely, but anyhow. And so we had to start troubleshooting the machine. Actually, the other problem, I guess I could go into it. The first thing, if you're doing any troubleshooting or teaching, don't go in the back of the machine and take everything out and inspect it all and put it all back in, because that's what they did. They took out every single circuit board in the machine. They put it all back in. They failed to look and see if any of the cables were marked or labeled, which they weren't. And they couldn't get the machine to run and were in a big sweat because they were writing this manual with all these people there. They flew me out the next day practically, and I had to troubleshoot everything, including not getting it started. And there was no drawing. Haas made no drawing for this power-up circuit.
There's a mediocre joke of a drawing.
Yeah. So we made a drawing by hand of this logic, and then the Army took it in and made his beautiful drawing for us.
We've modified it and changed it a little bit since then. We don't have their exact drawing, but here you can see this is available for free download. So I want to make it easy for people. I have told people about this drawing, and they download the drawing, and then they're clueless.
Yeah.
I can't teach everybody how to troubleshoot difficult electronics.
Well, or how to read a schematic if they know nothing about electrical components. So yeah, that's difficult. But if you have some savvy of electronics and schematics, this will help you troubleshoot this way easier,
much faster.
Well, we tell customers when they call and ask about buying a new machine, the first thing I ask them is, does it come with the manuals? And if they say, well, we don't know, and I said, well, you better get them because
Or a used machine.
Because it's going to take us 10 times longer to solve your problem without the drawings.
Let's walk through the drawing. The way I learned.
Well, here, if it doesn't come on, then they're going to check first.
Yeah, this is an easy one. So I went and turned the machine on, pushed the button, and it doesn't come on.
Yeah.
I learned this from you as a little kid with cameras. The first thing you check is the power.
That's right.
The battery. If something doesn't turn on, it's a no-brainer.
Don't go looking at some complicated problem. Check the power.
I have told this to people, and they brought in an electrician, and the electrician doesn't know how to check the power, and they're confused. Let's go back and check power, and let's do it the way you taught me, which is not that complicated, but most people don't understand it. How to check the incoming power. Because
first thing they do is measure it from ground to one of the legs, and it doesn't matter.
Especially when you've got a rotary phase converter, or you've got a solid state converter, that can really confuse you when it comes to power. So if you're behind your machine won't turn on. The most obvious and most simple is you don't have good incoming power. Right. So let's start at the top of your breaker. Let's put your voltmeter in AC mode, and we're going to check the 3 incoming lines at the top of the breaker. So if I stab this in here, we have 250 volts, and this is tricky. My meter auto ranges, and so you've got to look at the line at the bottom. Yeah, here, see. Okay, wait. There we go. You've got to look at this line at the bottom, and does it say volts, millivolts, microvolts? Because if I pull this out, look, I'm reading 20 volts, 18 volts, 6 volts. So that's just randomness of me just touching things in the air. It can be confusing. You need to read on your meter what is the actual voltage. So I've got 250 between leg 1 and leg 2. I'm not measuring to ground. Then let's go from leg 1 to leg 3. 249. We take the third meter lead, and I'm going to put it over. 251. That was on the top. Now the next thing to check, Dave's got a story about this. What was that machine Daniel Petrie worked? It was a new machine, and it would randomly turn off when the spindle started. It was out in North Idaho.
No, that was it.
Was it in Spokane?
Mountain.
Was it in a mountain?
The one with the 5 volts shorted out?
No, this was the one where there was a loose wire.
Oh, no, that was a Fadal. It was in Montana.
Oh, okay, maybe it's happened more than once.
I got the picture of the lightning bolts coming off of the arc.
What I have seen, this happened down at Airway Heights here. The machine would randomly alarm out, and we were there one day troubleshooting it. We had been there 4 or 5 times. We'd get there, the problem wasn't happening. And we were poking, and we saw some arcs. And we went, wait a minute. Turn off the breaker, check the power was off, tightened on every connection. Multiple connections were loose.
Yeah, loose wires.
Loose wires. So that's something to keep in mind. So back to troubleshooting this. Machine won't turn on. I checked the 3-phase power coming into the top of the breaker.
Yeah, let's check it to ground so you see what people do when they don't understand.
So I'm measuring one leg to ground, 120 volts. Is that good or bad? I don't know.
Check the next one.
217 to ground, 120 to ground.
There's a reason why we don't have to get into it, but it doesn't matter. There's nothing in this control cabinet that goes from one of those legs to ground.
Everything is on the 3-phase and then through the transformer. Mm-hmm. After the transformer, that gets more electrically complicated. We'll make videos about that. But you shouldn't be measuring to ground when checking voltage. It doesn't matter. The machine just needs straight 3-phase.
So check the other side.
So now we need to check the next side, because what if this breaker has a problem? Now the breaker, we could turn the breaker off, and let's check. Okay, 0.4 volts. Let's turn the breaker on. What if we have a bad breaker? I have seen bad breakers. So 250 from leg 1 to leg 2, 248. Okay, 250. So incoming power has gone through the breaker. The next thing to check is the top of the contactor. So this is the main contactor right here that turns this whole machine on. So if we're working our way down the drawing, we've checked the main incoming power on the top of the breaker. We've checked the bottom of the breaker. This is the symbol of the breaker, and it's closed. Now we work our way down, and now we're going to check right here. This is labeled as the K1 contactor. Now the K1 contactor is right here. Now in newer machines, it can look a little different, and there's a metal bracket or cover in front of it. You're still going to want to check the power, because what if you've got an open wire? So let's check the 3 phases going to the top of the contactor. 250, 248, 250. So looking at this drawing, we know we've got power that's getting to here, to here, and to here. When you push the on button, nothing happens. So let's go push the on button, and let's look back here. This is a good troubleshooting step. If you've got 2 people, have one person in the front, push the on button.
Okay, it's on.
Nothing's happening back here. Nothing's happening. So let's work through this electrical schematic, and we're going to trace it at every step. Coming off of the 3-phase that comes in, it's tapped on these 3 lines, and we can look at it right here. We've got this wire, and this wire, and they tie in right behind here. And I just measured the voltage there, so I know there's voltage there. And if I was to follow it to this plug right here, let's do that. Hold that for a second.
Where's the on switch?
Let's go ahead and just check. I want to check every point through this circuit so you see how I'm checking it. 250, 248, 250. So we are getting power to right here at P25. Now, on this schematic, I'm going to show you some things that you may not know. Things inside of boxes in the machine tool world are either options on the other side of a terminal strip or inside something. So this box shows everything that's inside of the K1 contactor. This box is showing everything that's in the power distribution board. This box is showing everything that's on the I/O PCB, and this is showing everything that's on the operator pendant up front where the push button is. And in between these two, we have a conduit, the wires leaving here and going all the way to the front. So let's just do a quick walkthrough, and I'll show you everywhere this circuit goes. Power comes in, it goes to a transformer. Jumps to the other side of the transformer is 24 volts AC. On the other side of that transformer, one leg of it is grounded. The power on the other side comes back to the power distribution card, goes to the K1 contactor, goes through the coil of the K1 contactor and comes back to the power distribution board. Then it splits right here. This is important. It then goes all the way to the pendant to the on button and splits and comes down to the K1 contactor. It goes through a normally open contact. Now here's a trick I learned from an old guy who worked on submarines. He was a great CNC tech. He beat this into my head every time we worked somewhere. Aaron, what do you remember? All electrical schematics are always drawn in the non-energized state. And I tell that to our techs. Remember, everything is drawn in the non-energized state. That helps you in troubleshooting because this is open. This is open. This is not energized. So when we look at this, we can say, all right, if it's not energized, it's open. So carrying on with our circuit, we know the power came down, it's split. It's not energized because it's drawn that way. It then comes back and it also goes up front to the off button. The other side of the coil, which is the other side of the contact, goes to the on button. So we've got these two voltages, which come from the transformer, going up to the front. Then it leaves the front and comes back and goes to a plug on the I/O board. Remember, everything is drawn in the non-energized state. So a normally closed contact, K7, means that when it's energized, it's open. But when it's not energized, it's closed. It's a normally closed contact. It then leaves and goes back to the ground. So in troubleshooting this, we've got a difficult task of chasing the voltage. Somewhere in this circuit, we're losing voltage and something's not working right. But you've got to know where to put your voltmeter lead, where to measure the right voltage. Because if I just put it to ground or if I measure the incoming power, I'm not going to be measuring the right circuit.
Well, we know this isn't pulled in physically.
We know it's not pulled in. A trick that I like to do when I'm troubleshooting a power on circuit problem is I hold the on button on. Because if there's a problem with the latching circuit, because this is a basic latch circuit, the on button should latch it and it should stay on. The off button should kill the latch or open it. So if the on button, holding it down, keeps the machine on, you know that this portion of the circuit is working, but something in the latch circuit is not working.
Yeah.
In our case, we know the power gets to here at P25, and it then leaves to P24 and goes to the transformers. So let's check the power going to the transformers and the power coming off the transformers. So that's going to be P24, and if we look right here, and you got to be a little careful because we have live voltage up here. Here is P24. No. Let's see what we got here. This one and that one. These are not always labeled correctly. Our drawing is not perfect. No surprise.
Well, our drawing, you need a light in it.
Yeah, the light's great. There are different, like we spoke about in the other video, different power distribution cards have had different plugs. Our drawing is close, but you're going to have to look at it and say, all right, I'm going to have to look and see what makes sense. So we've got this transformer right here plugged into there, and we've got this transformer plugged in right there. Two different transformers. I'm not sure why they have two different transformers. I know some machines had two different transformers and a jumper, but we don't have any jumpers here. Let's see. This one says work light, and I don't see, let's see. That one says 2T5, and this is labeled T5. So we've got 5 plugs here, and we know that the plug, if this is labeled correctly, the 2 on this side should be the incoming power, and the 2 on that side should be the, oh yeah, that's great, should be the local. So let's check and see. I've got my voltmeter. I love these stab-in leads. If you're doing a CNC machine troubleshooting, the stab-in leads are great. 250. Okay. Now let's check these two. Okay, nothing on that one. 28 volts DC. Now, we got a 24 volt system, but our machine...
24 AC.
24 AC. We're feeding our machine with 250. It's totally acceptable in this system that you would have 30 volts, 28 volts. I would be concerned if it's below 22, below 20. You've got low voltage somehow feeding it. But we've got 28 volts DC. I'm going to leave my leads there. Let's talk about troubleshooting this a little further. And chime in if I'm saying something wrong. we can follow this circuit and we know, okay, if I'm measuring 28 volts and this is tied to ground, I should be able to pull one of my leads out and touch the chassis and leave the other one there, and I still should have 24 volts. And then I can work my way down the circuit with reference to here and say, is there voltage on this side of the coil? Is there voltage on this side of the coil? Then I can say, is there voltage on the top of this contactor? And we're going to work our way all the way down, because there should be voltage through the coil, and there should be voltage here. And then there should be voltage all the way down to here, but there shouldn't be any voltage there. So I work my way down, and where I expect to see voltage and I don't is where the problem is. Sometimes you can cut the problem in half and say, is the problem here or is the problem there? But you've got to know this circuit really well to cut it in half, and I want to work my way through the circuit. When this works correctly, the on button turns the machine on and it stays on, and the off button turns it off. It's called a latching circuit. The on button turns it on and keeps it latched. The off button breaks the latch. We're right here in our circuit. We've measured the power going to the transformer, and we're measuring the power coming off the transformer. We have 24 volts. That power comes back onto the power distribution card, goes over and goes to the coil. Now the coil is going to be the portion of this K1 contactor that sucks it in. When power, electrons, current flow through that coil, it creates a magnetic field. That magnetic field sucks in the contactor. We're going to follow the voltage to the K1 contactor and make sure if this contactor wasn't getting any voltage from a bad cable, a bad plug, or from here, then the machine wouldn't turn on. So we're going to go to this P23, and we're going to try to measure from this reference to here and see if we have voltage. Now we could even jump right to the coil of the contactor. So if I go P23, let's look here. Which one is P4, P3?
You're on P5.
P23 is what goes to the, looking for these wires right here, and they go up.
Just measure the
Cable.
volume of the contact.
Yeah, we'll go to the bottom of the contactor. Okay, 67 and 66. If I look right down in here in the bottom of this contactor, it says coil. So I'm going to measure one of these. Hope my meter auto turned off. Okay, I've got 13 volts there. 13 volts there. That's half of my 26. There's 14 volts there. There's 14 volts there. And I'm measuring from here the 28 volts. So what I'm doing is I'm measuring from here. From here and here, I've got the 26 volts. Now I should have the 26 volts there, and I should have the 26 volts there, and I should also have the 26 volts up here at the power on circuit. So let's just do some more probing and figure out why we aren't getting that. Let's do some looking around. Okay. Those two wires right there. There's 28 volts. Well, I see where 13 volts. No voltage. Oh, that plug was tons of one. This is why these pins are really nice. There's the 13 volts. 13 volts. I don't have a good explanation of why it's 13 volts. I would expect, unless it's grounded and I'm measuring pre-ground, see I've got 14 volts on all of this. Sometimes when you're troubleshooting, you don't know the answer. There, that's what I expected to see. 28 volts right there. So that's measuring on one of the plugs. I just want something to point with. I've got 28 volts between here and one of the plugs that's going to the K1 contactor. And that one, it looks like, is the white wire, which here they've labeled as red and black, which is the case down there. So let's just see. I could be totally going in the wrong direction. Okay, it's got 2 other wires that come off.
Measure the coil. Forget all the rest of the connectors.
Yeah, let's go to the
Or
coil.
go all the way to the switch, and then you can bypass a bunch of stuff.
Yeah, but remember, that should be grounded separate from, because if we have a problem somewhere in this side of the circuit, it could change the voltage reading that I'm getting here. Because if I'm measuring here and here, I've got the same voltage, and it's just the same wire.
But even to the coil, it's the same wire.
Okay, the circuit is confusing. It's, if I measure on the red...
Actually, because they're switching on the output side of the coil.
Yeah.
You know what I mean? They're switching way down here when you hit the power on.
So, I can't, if I was to stick my voltmeter on this coil and measure voltage, that's kind of useless. Because I'm measuring...
No, I know. Just one side of it.
I've got to measure... Well, I can't measure voltage across it. It's a coil of wire. I've got to measure voltage reference to over there. And I know I've got the red and the black. So let's try this again. 13 volts. 13. Oh, let's see if that makes a difference. Okay, 28. 28. All right, I need to take a back up and explain to you what just happened. I sabotaged this circuit and to make this video, and the sabotage messed up my voltage reading. And so I'm sitting here going, why doesn't this work? Why doesn't this work? Tipped me off to, would have tipped me off to a problem further down the circuit. What I did to make this machine not function is I disconnected this plug. This plug is on the I/O board and is what automatically turns the machine off. If the machine has an overheat, if it has a vector drive problem, or if it senses a short, it can turn itself off by sending power while it's still on to this relay. This relay, when it's energized, opens. When it opens...
Oh, it's closed. That's why.
It's normally closed, which messed up my voltage reading. So if you were doing this and you're like, I expect to see 28 volts. I expect to see 28 volts. We can pretty much say there's a problem somewhere. We've got resistance or we've got something that's not correctly grounding. That was a fun troubleshoot. The voltage didn't make sense and it was because I sabotaged it. Now we'll continue down this thing, but it's a great example that we should have seen 28 volts there. We didn't. We should have kept going down that circuit until we found the 28 volts and we would have found our problem. But back to how...
You could have had a problem on the I/O board and had the same problem.
You absolutely could have. But I'm trying to, in this video, show how to correctly troubleshoot it, and my voltage reading didn't make sense.
Because you had... But if you had the problem here, you would have the problem you're seeing.
We would. And I would have continued down the path of going, well, this doesn't make sense. Let's go to here. This doesn't make sense. Let's go to here. I hope I would have eventually found that problem.
You should have, yeah.
So back to here, this complex circuit, many people will just ask a CNC tech to come in and troubleshoot their power on circuit. And I've talked to a lot of people who are not Haas techs. I send them this drawing. They know how to read an electrical schematic. They've never worked on a Haas. They can walk in and pretty confidently troubleshoot a Haas because they know how power on circuitry works. Many machines, the power on circuitry is much more complex than this.
Yes.
They have a second ready button. They've got drives that turn on. So let's keep going. Okay, 28 volts right here going to this coil. So
this could be the problem next.
This could be the problem next if the machine doesn't turn on. So if I'm measuring here, going to the coil is black. If I measure down here, I've got 28 volts. If we measure on the other side, we've got 28 volts. So I've got my meter here grounded on this red wire, and I've got 24 volts here, 28 volts here, 28 volts here. That means I should have 28 volts on 69 on the black going to the contact. So let's check here. I've got 28 volts there. Now, if this normally open contact is functioning correctly, I should be able to not see any voltage here. And if I was to push this in, I should see voltage there.
And it would latch and boot up.
And it should latch and boot up. When you press this in, let's do it real quick. I'm going to put my voltmeter here Going to use an insulated screwdriver, and if I push this in, the machine, if it's functioning correctly, should latch. And now I've got no voltage across it because I'm measuring on the same line. If I was to change my ground reference, now I've got 28 volts. Okay. If we
Which now means you probably have an on switch problem.
could mean we have an on
Or an off.
problem. So we can run to the front of the machine. Let's go do that, and we'll check the resistance. Yeah, push that around this way. Oh,
On the way?
it doesn't matter. This will swivel all the way. You just started to swivel it multiple times. There we go.
They're going to be looking at the back.
Oh, let's flip it this way. I think it'll go further this way.
Oh.
Look at there. All right. We've got our two buttons up here. Now, you can't really check voltage up here because we don't have the correct reference. If I was to check with my voltmeter, okay, that's kind of useless. Let's check over here. Okay, we've got 28 volts
That's because that's open.
across.
On?
That's the on button.
Yeah, that's open.
So we got 28 volts across that one. Now let's just for kicks check and see. I'm in resistance. That one's open, which according to this is an open switch. So that reads good. And let's read this one. This one reads closed. And if I was to push it, it should change to open. Okay. And if we come over here and check this one, which is a normally open, if I push the button in, it should change resistance and measure 0.
You can measure resistance to that medium the power is on it?
Yeah. We're at 28 volts. I don't think I would do it with 480. But yeah, I have that. If you start getting into DC voltage too high, it'll backfeed and you'll have negative resistance.
Okay.
I'm looking just for opens or closed. I think
You
I
don't
think-
do that on an old analog.
the Simpson
Simpson
60.
Doesn't work.
I think this calls for another 2-hour video, probably, to go through everything in this circuit and check it all. I think I underestimated how long this could be.